start? All right, picking up where we left off on electron configuration. First of all, we need to know this definition of polyelectronic atoms, which is basically everything besides hydrogen, because it's anything that has poly means more than one electrons. Okay, so only hydrogen is not polyelectronic. Okay, but basically when we're talking about this, remember when we have, as soon as we start adding more than one electron, we have electron repulsions, because like charges repel each other, so the electrons get too close and they're repelling each other. So the effect of these repulsion is to reduce the nuclear charge or the pull of the nucleus. This is what we're going to be referring to as the effective nuclear charge. We did talk about effective nuclear charge in the first year of chemistry, but it's going to be a little bit more important in this unit for AP chemistry. Also, as we are adding more electrons, we have something called shielding, and shielding is basically the electrons in lower energy levels help to shield those outer valence electrons from the effect of the nucleus. Usually when we're talking about shielding, we're talking about, usually, not always, but usually we're talking about the inner core electrons and the outside electrons, because shielding is not as big of a deal in the same energy level, although there are times that we'll see today that it does have a little bit of effect. And this is just a good visual kind of to show you what that shielding is. I didn't show you all that in Chem 1, we just talked about it, and we, but that is kind of a good, I liked that picture actually, I thought it was a good one. Okay, penetration effect is where your electrons can get closer to the nucleus in some levels than others. So the electron is temporarily closer than it would normally be. Of course, the S levels, because they're smaller, are going to have a higher penetration than the big, giant F ones. And so the orbitals, because of this, will fill in order of increasing energy. So because of these S electrons having a greater penetration, then they are able to fill before the 3D. So that's another reason why 4S fills before 3D. We always just say because it's a lower energy level. This is telling you why is a lower energy level. Okay? This is just those three of those things put together, including Coulomb's law, which we will be referring to. And so those are things that we're going to be talking about as we go through periodic trends. Just to remind you which ones are valence electrons, which ones are core electrons. This is a no-brainer for you guys. I just thought I would mention it so you can't say I didn't tell you. Of course, the outside, upper, higher S and P orbitals are your valence electrons, and then your core electrons are the ones that are underneath. And then if you have not already watched the electron configuration, now in AP Chem we rearrange and put them all with the same energy level. They didn't do that here. They should have. This 3D should be over here with that to help you recognize that. Okay. Two terms that you have not heard before is paramagnetism and diamagnetism. And paramagnetism is you have unpaired electrons and they are attracted to a magnet, hence the magnet by the unpaired, like my little visual there. And then diamagnetic has all the electrons paired, and they are actually repelled slightly by a magnet and not attracted to it. Okay, so when you're looking at your periodic table, you can figure out just based on where they are if they're diamagnetic or not. For instance, zinc would be diamagnetic because all of its electrons would be paired, as would all of your noble gases. They're all paired up, right? There's other ones on there, but I'm just saying very quickly, you could say zinc is going to have 3D10, 4s2, everything's paired up, so it'd be diamagnetic, so it would not be attracted to a magnet. Does that make sense? Everybody staring at the periodic table. Okay, isoelectronic, this is going to come up twice today, but basically, I mentioned it in the video, isoelectronic is if it has the same electron configuration as something else. When we're forming ions, they're going to be isoelectronic with either, if they're a nonmetal, they're going to be isoelectronic with the noble gas that comes behind it. If they're a metal, they're going to be isoelectronic with the noble gas that comes before it, because the metals are losing their electrons so that they have that octet in the in the last outer shell. Okay, but size will not be the same for them because of the number of protons. So I'm looking at this one here. They are all isoelectronic with neon. And then if you look at the size difference, oxygen is isoelectronic with neon, but it has less protons in the nucleus than, say, does fluorine. So fluorine's a little bit smaller because it has a higher effective nuclear charge. And then same thing when we get over here to sodium and magnesium. Even though they're all isoelectronic with neon, sodium's going to be slightly bigger because it has one less proton than magnesium, so it has a lower effective nuclear charge to pull in those electrons. Okay? Any questions on that? Is it all making sense so far? The groups of the periodic table, as far as their properties and common properties, I expect you to read that on your own. I'm not going to sit there and read it to you and remind you that noble gases are not reactive and alkali metals are the most reactive metals. Y'all can read all that. It's not worthy of our time in class. All right, so that brings us to a trend, which is worthy of our time in class because they like to ask questions about this on the AP exam. And there are several different arguments you can use, but you have to use the right argument in the right situation, which is the difficult part sometimes for you to discern. Okay? So here are the trends. We'll talk about each one, just like the pretty colorful picture. Here are the arguments that we will be using throughout these, and you have to apply the correct argument to the correct scenario. First one is effective nuclear charge, or ZEF. Most people go ahead and just say effective nuclear charge, but if you did say ZEF, you're probably okay with that because that's what that means in chemistry. But basically, the more or the higher the effective nuclear charge, the more positive the nucleus, the more attractive force there is for the nucleus for the electron that they're holding in place. And we want to relate this to energy whenever possible. So we would say, for instance, that if we're looking in the same period, let's look at period 2 and lithium to fluorine, we would say that fluorine has a higher effective nuclear charge, therefore it would require more energy to remove the electron, thus giving it a higher ionization energy than lithium. And that's how I would say that. No extra words, don't be wordy, okay? This test usually takes me a long time to grade the free response because y'all get really wordy, okay? So let's try to not be too wordy so I can grade it faster, okay? Second one is distance, and of course we can always relate that back to Coulomb's law too, because if I have a greater distance from the nucleus, then my R value on the bottom is greater, which means my attractive force goes down because it's further away. Okay, so again, we would also relate that to energy. So if I was looking at lithium versus rubidium, and I wanted to talk about ionization energy, I would say rubidium's valence electron is a lot further away from the nucleus. Because of the distance, and Coulomb's law would state that it would have a lower attraction, so it would require less energy to remove the first electron from rubidium than it would from lithium. So that's a way you could word that. Shielding, of course, is the core electrons. Mostly we will use shielding, I think your notes say don't use it ever in the same period, but that's not true. There are some outliers, and it is because of slight shielding. But mostly when we talk about shielding, we are referring to the inner core electrons. But Coulomb's law is always a better argument than shielding. Okay, some teachers don't even teach shielding, but because we talk about it in pre-AP, I want to bring it back so you can relate to what we learned the previous year. And then the fourth argument is if something is going to minimize electron-electron repulsions, that puts that atom at a lower energy state. And makes it more stable. So we would, again, relate that to energy whenever possible. It's all about the energy, okay? Okay, so now for the trends. Periodic trends are actually one of my favorite units because I love the way it all fits together. And oddly enough, we're covering that in pre-AP right now. Not quite to the same level as y'all, but they are covering. Although I did bring Coulomb's law into them for them this year. So ionization energy is how much energy does it require to remove an electron? Or how tightly is that electron bound to the nucleus? The units are going to be kilojoules per mole in most cases. They are positive values because we have to put energy into the system to remove it. So it's an endothermic reaction. It depends mainly on two factors, the nuclear charge, or effective nuclear charge, and the distance. Those are the two things we're going to be looking at. So the lowest energy valence electron is removed first, and then successive electrons take much more energy to remove because now the atom has a positive charge, because now we have more protons than electrons. So here is what the formula for an ionization energy looks like. This would be the first ionization energy, so that would be to remove the first electron, okay? And then second ionization energy, still only removing one electron, but you would have to remember to make that positive because you're taking one away. Okay? Okay. And then here is a table of period 3 and their first, second, third, and successive ionization energies. And this is a popular question actually on the AP exam as a multiple choice. They'll give you a series of values and ask you how many valence electrons this unknown atom had, and you will look for the giant jump, because there is a giant jump from when you cease taking valence electrons and begin taking core electrons or inner shell electrons. So in the case of sodium, I mean, it's just a big jump right there. But if you look right here at magnesium, you say that's about double, and then a big giant jump. So you would look at that and say, well, that most likely had 2 valence electrons. Here's aluminum. You've got the 3 here, 1, 2, 3, and then big giant jump, because now you're starting to take in the inner shell or core electrons. So if you see a data table of successive ones, find the big jump, and then that's where your valence electrons were no longer being taken. It was now core electrons. And for some reason, kids miss that question a lot when we first start doing it, and I feel like it's fairly straightforward, so I don't know why. Also, here is the ionization energy for several of the periods. This is period 1, 2, 3, 4, 5, 6. And as you can see, the general trend is to increase. There are some blips right here and here. We'll talk about those blips here in a second. But you see what happens here is, as I am increasing my effective nuclear charge, so my nucleus is effectively getting stronger, my ionization energy is generally trending up. Then what happens between neon and sodium? What did I just do? Huh? I added a new shell or a new energy level, which now means that valence electron is further away from the nucleus. So the ionization energy drops back down and then continues that general trend going up. New energy level drops back down. So that lets you see that visually. And we'll talk about these little blips down here in a second. Okay? So here is the general trend, and when we're talking about these general trends, we are basically only talking about the S and the P blocks, okay? Because in the D blocks, why does it not affect those trends as much? Why do you think? There's slight changes in the D block, but they're very slight compared to S and P. And why would you think that is?
Because they're not in the outer?
That's exactly right. They are not in the outer valence electrons. When I'm filling the D, so for instance, if I'm in period 4, right, and I filled up the 4s, then I'm dropping back down and filling up that 3D, and that's all fairly consistent. And then I go back and start filling up the 4Ps. Okay? That's all in your notes. Here are some of your exceptions. We saw those in the graphic of the group 3 and also group 6. The group 3 exceptions are because of the shielding, the slight shielding of the two S's. So group 3 is going to be S2 P1, right? All of group 3s, that's their outer electron configuration. And so this one P electron right here, why is it not writing, is slightly shielded by those two S ones, okay? The group 16, or group 6, or it is group 16 on here, when they say group 6, they're meaning 6A, which is 16. So let's make that a 16 so you don't think it's actually group 6. If you look at old periodic tables, they say groups 1A, 2A, and all that. I don't know anyone in Connecticut. I'm not going to answer that. Okay. In group 16, the difference is here's going to be S2 P4, right? So if we look at P4 and we draw that out, it's 1, 2, 3, 4. And what happens is there's electron-electron repulsion happening once I pair it up. If you haven't watched the video, then you're looking at me very confused, I think. So that's your you just gave away your tell.
No, just don't know.
I should call out the people who gave away their facial expressions, gave away their tell that they have not watched the video. Okay. But I won't say any names that maybe start with an A and maybe start with a T. I'm just saying. Anyway, because of that first pairing up, there's some electron repulsions, which lower the energy level just a little bit, and so it's easier to take that electron away because of that electron repulsion. When I start adding the other ones, it overcomes those repulsions by the effective nuclear charge. Okay, so that's basically what I just said. So read it if you didn't understand what I said, or better yet, go back and watch the electron configuration video first, and then come back. Okay, same thing with that. So that brings us to atomic radius, which is size, and that is obtained by measuring the distance between atoms in chemical compounds. We can't actually measure them directly because they're too small. So here's the general trend for that. Same reason that the trend is the way it is for ionization energy. It's the way it is for being smaller, because as I go across a period, my effective nuclear charge is getting stronger, so it's able to pull in those electrons tighter, making the atom smaller. Okay, and then as I go down a group, I'm adding energy levels, which obviously will make it get bigger. Atomic radius trend going across a period is the ones that kids struggle with the most, because it seems counterintuitive. I'm adding more stuff, I should be getting bigger, but I'm adding it all in the same energy level. And remember, my protons are in the nucleus acting basically collectively as a group, but my electrons are spinning around all by their little selves out there in the electron shell. So here's your trend there. It's exactly the opposite of ionization energy, but it's exactly the opposite for the same reasons that the trend is that for ionization energy. Ionic radii is... I don't really care about the trend, or they don't really care about the trend as much as, do you realize that cations are smaller than their parent atom and anions are larger? And I'll go back to, gosh, the unit where we were drawing particulate diagrams, and that was one of the things is when you're drawing them in a particulate matter, you always want to draw your cation smaller than your anion. Okay? And we had the example in the notes of sodium chloride, excuse me, whoa. And we drew sodium much smaller than we do chloride because of where they're located. Okay, and their anions are larger, cations are smaller. Okay, again, when we're talking about being isoelectronic, we're going to look at the size and how many protons they have. So oxygen is isoelectronic. Oxygen ion would be isoelectronic with fluorine ion and also neon, but because oxygen has fewer protons, it's going to be a little bit bigger than fluorine. Don't say because it has 2 more electrons or it has an extra electrons, okay? Because if you're looking at oxygen, you think, oh, it took in 2 electrons, so it's going to be bigger than fluorine, which only took in 1 electron. It's not a valid argument. The argument is oxygen has 1 less proton than fluorine, thereby decreasing its effective nuclear charge, so it would be a larger atom. Electron affinity is the opposite of ionization energy. Ionization energy was the energy required to remove. Electron affinity is the energy associated with the addition of an electron to a gaseous atom. So it looks like this. Okay, it looks the opposite. We've got the electron, we're adding it, so it's a reactant, and then we're going to make a negative product. If the addition is exothermic, the EA is negative. So these you have to think a little bit backwards. So if it's a large electronic affinity, it's going to be a large negative number because it's releasing that energy whenever you add the electron. Okay. So what would you expect to have the highest electron affinity on the periodic table? Huh? Fluorine. Yes. Yeah, because it's the smallest. So the nucleus is going to have the greatest effect on the things because they can get close to it. Okay, so here are some values for you to look at. So here you go. There we go. But actually, believe it or not, it's chlorine. It's a little bit higher. Yeah. But fluorine is a very good estimate. Yeah. And of course, we see on the noble gases, they don't have really an electron affinity because you're going to be hard-pressed to add an electron to a noble gas. And there's the trend. It is the same for ionization energy, but generally there are a lot of exceptions. You are not required to know those exceptions. You might be expected to explain the differences in the trend based on where they're at, but you don't have to know the exceptions. When they redesigned the AP, there's very few things they actually want you to memorize, like exceptions to the rule. Just like when if you watched the video and I told you about the exceptions in electron configuration, you don't have to know that they're exceptions, but if they ask you a question about it and say, why is this way, you have to be able to explain the why. Electronegativity is defined as the ability of an atom within a covalent bond to attract electrons to itself. So the difference here is we're talking about when I'm bonding things, which one is the highest electronegativity. And that is definitely important in the bonding unit because the one with the greatest electronegativity is the one that gets the electron, either taking it or it shares it and it gets it more often, making a polar compound. Okay? Non-metals are going to not have a high electronegativity. Non-metals have a high electronegativity. They want them. And metals don't have a high electronegativity. Because what do metals like to do with their electrons? Give them away. Yeah. Bye-bye. Okay. They actually don't like to do it. They don't have feelings. They don't have wants and desires. So never say that on an AP exam. Metals love electrons and hate or whatever. Don't give them animate feelings, okay? We say that as ways to help us remember, but don't ever say it on an AP exam. Don't say, happy little campers, 8 is great. I mean, I tell you all that in Chem 1, but yeah, we don't personify our elements. They don't have feelings. They should. They're excellent, but they, Here is your electronegativity values. If you recall from Chem 1, if I see you 20 years from now, if I ask you what the most electronegative element is, you better tell me fluorine, right? Fluorine is the most electronegative. Actually, fluorine is assigned a value of 4, and everything else is relative to that. Linus Pauling developed the scale many years ago. He won a Nobel Prize for it, actually. Also, he's, I think, the one that discovered that vitamin C is important for not getting a cold or something. I don't know. He has something to do with vitamin C. I don't remember. Probably should know that. Linus Pauling. He was an American chemist. Huh? I just sign it a 4, and then I guess based everything else on that. Okay. There's the trend, same as ionization energy, excluding the noble gases. The higher noble gases like krypton, xenon, and radon, they do have an electronegativity because they're big and they can share. Because they have big shells. But your heon, I just made up. Helium and neon is heon. And argon, those 3 do not have an electronegativity value. Heon. I'm going to have to come up with a joke with that. Okay, here we go. Never state the reason for the behavior is because that's what the trend says. That is 0 points, and I will make fun of you if you say that in here. I will write you a nasty little note on your paper if you say, the trend says this. I will, even if you say the rest of it right, I'm still going to count it wrong for you saying that's what the trend says. Okay? Yeah, don't say it. Okay? That's how serious I am about that. Here are some hints when you are answering these questions. First is to state that that's the trend, and then that's no points. Don't do it. Okay? Second point is, and this is on anything, not just periodic trends. This is on anything. If they ask you about 2 things and ask you to compare or ask you why that's boiling point or anything, you must discuss both things. If you only discuss one of them and you think, oh, well, they assume that this is the reason why for the one, that I mean that's not the reason why for the second one. That is like a big thing in AP Chem. Discuss both that they're asking about. Okay? All right, practice. We're almost done. The notes. Okay, practice. First ionization energy of phosphorus is 1060, and that for sulfur is 1005. Why?
Because the trend says.
Tyler Moss, I'm giving you a negative shout out on the video. That's your 2 negative. That's 2 negatives for you. The 2 negatives in here don't make a positive. Why so? Why is, if you look at it, sulfur comes after phosphorus, so you would expect that it would be increasing, but it's a slight dip. Why is there a slight dip in the ionization energy?
Because it's group 16. And those
Because it's group 16 is not a reason.
They have the up and down and then 2 ups.
So phosphorus is a S2P 3, right? And sulfur is S2P4. So in that P shell, 1, 2, 3, 4, it's our first time we've paired it up. And what do we have when we have two electrons? Electron-electron repulsion. And so because of that electron-electron repulsion, there is a slight decrease in the energy because it's trying to minimize that repulsion. And so it becomes, takes less energy to remove it. I can say it again, or I could refer you back to the notes where it said the exception. Like it talked about oxygen and sulfur. I mean, I'll say it again, but if you want to know how to write it like the notes explain those exceptions. Does that make sense what I'm trying to say? I didn't mean that to sound rude. I just meant to say that's worded a lot better than what I'm saying it. But because it's paired up, you have an electron-electron repulsion in that first one. And so it's trying to minimize that. So it makes it a little bit easier to take it away. Okay? Okay, we're going to let Adam answer these three. Identify these elements, Adam, based on their electron configuration. I'm just teasing you. What ends in 2p6, everybody? Neon. What ends in 3s1? Sodium. And what ends in 3s2? Magnesium. So there's our elements based on their electron configuration. So which one would have I'm going to ask Max, which one of these would have the largest first ionization energy? Neon. Thank you, Natan. Neon. Largest first ionization energy. Why? Because the trend says so. I'm gonna just.
It has a full outer shell.
Not because it has a full outer shell.
Because that's a good question. Which atom has the largest?
Okay, let's think about the outside electrons in neon. First of all, what's the difference between?
The smallest atomic radius.
That's not the reason why. It has one less shell. Thank you. So it is closer to the nucleus. So that electron would be harder to remove. And then the next highest ionization energy would be why?
Well, I'm going to say the atomic radius again, but that's going to be wrong.
Is it because
No, you cannot. You can't use one trend to explain another trend.
It has one more proton?
Well, you're incorrect. Magnesium would have the smallest ionization energy.
Wait, but I thought it was...
So, but now, okay, so the largest one is going to be neon. Now, between sodium and magnesium, which one would have a larger ionization energy? Huh? Magnesium. And then, oh, sodium's the smallest. Did I say it backwards?
No.
Okay. Okay. All right. But never use, I'm actually glad you said that, Josh, because you never say it's got a higher ionization energy because it's got a smaller radius or whatever. You never use one trend to explain another trend. Go back and refer to where is that electron located in conjunction with the nucleus. Okay? And then predict the radius for the following ions. Let's see, do we want to go, let's go largest to smallest. It doesn't tell you which way to do it, so I'm telling you go largest to smallest. Big to little. So if I'm going largest to, biggest, yeah, largest to smallest, which order would I be? It's just backwards.
Big to little?
Big to little. So strontium would be greater than calcium, which would be greater than magnesium, which would be greater than beryllium. And in this case, the fact that they're all 2+ ions isn't going to affect the size as much as the energy levels, because each one of those has, this is in period 5, 4, 3, and 2. So it has that many more energy levels. Okay? Then that brings us to the last thing for today, and that is photoelectron spectroscopy. You saw a little bit of that in the Bozeman video we saw the other day. Uses energy emitted from the light to see how many electrons are being kicked out. It doesn't make that noise though. Okay. Very high energy photons give off the wavelength, and since there are limited number of electrons, there are limited number of energies that they can be emitted. So here is what a photo electron or a PES looks like, and it ranges from ultraviolet to X-rays, depending on the energy. And we saw that picture yesterday. But basically, because we've already seen this, I'm going to let you read through that. But I want us to label this. Okay, and remember yesterday, or not yesterday, when we watched that video, I said pay attention to the scale, which way it's going. In the video, they said 0 to 10. This one's backwards. Okay, so your highest energy end is going to be that's closest to the electrons that are closest to the nucleus. So because this is the high energy and this is the low energy, we're going to literally start counting. We know that this is going to be right next to the nucleus, so that's going to be 1s2. And then what comes after 1s2? 2s2. What comes after 2s2? 2p6. What comes after 2p6? 3s. So our last peak is 3s, so we need to see, is this a 3s2 or a 3s1? Well, if it was a 1, it'd be half the peak, so it's a 3s2. So this element that it's showing you the PES for is what element? Magnesium. Plus it says it on your paper too if you looked ahead. Yeah. But that's how you do a PES diagram. I think that we're doing a worksheet or whatever on that tomorrow if you ought to practice this, but this will show up on the AP exam. I think I told you all the other day it was question 4 last year. And it's fairly easy if you know how to do it, but there's some teachers that don't show it. Like my friend's kid didn't know what it was. They're like, I'd never seen that. Okay, the end for this lesson.